HIL test automation for safety critical systems, today with Thomas Schütz, CEO of PROTOS. My name is Anna Brotze, and I'm working at Hitex in Karlsruhe, Germany. Let me quickly tell you a bit about who we are. Hitex was established back in 1976. Since then, we've grown into a leading provider of development tools, certified software components, and services for development, production, and testing. And actually, this year is quite special for us. We are celebrating our 15th anniversary. Our motto is from 8-bit to AI, 50 years of embedded excellence. And our customers benefit from this experience. We provide support throughout the entire development process, from the initial concept all the way through to system implementation in both hardware and software. And we are particularly strong in embedded security and functional safety. We are proud to be a preferred design house for all major Infineon microcontroller families, and we are also an important distribution partner for HIL development tools. And last but not least, and this is the reason why we are all here, we can be your testing experts. Whether you are testing software modules with unit tests or combining multiple components with software integration tests, validate the entire software on the actual microcontroller using processor-in-the-loop or on-target tests. Or if you need to test and complete ECU with hardware in the loop or simulate the real-world operating environment with system tests. We are here to support you with tools for testing, with training to help you get the most out of the tools, or with testing services when you're short on time or staff. Or even with webinars like this one right here and now. So before I hand over to Thomas, just a quick housekeeping note. Feel free to ask any question using the webinar tool. Thomas and the Hitex team will get back to you via an email after the session. And when we wrap up today, you will see a short survey pop up. We'd really appreciate if you could take a moment to fill that out. Thank you. Our presenter today, Thomas Schütz from PROTOS in Munich, is about to give you a brief introduction to PROTOS and, of course, of himself before we get into the webinar.
Yeah, also a warm welcome from my side. I'm Thomas Schütz, and we're talking today about HIL test automation for safety critical systems. So what is it all about? Why are we doing that? The problem, to make it drastically, is in a situation like that. So you have two traffic lights in two directions of the same crossing. You want to avoid accidents. So lives are at stake. So that's something we want to avoid at all costs. So how are we going to do this? How can we avoid this in complex software and systems? The first question is, on which level can I test software for safety? Basically on all levels. Let's have a look at the different test levels. So we have a system here as an example with that controls a motor, a pump, a hydraulic system. For example, this can be a pump in a car or in a house, a water pump, an oil pump. Could also be a lubrication pump for technical applications. So, and there are many applications with pump systems that are safety critical. For example, lubrication pumps in a crane, in an airplane. It's very clear why we have a safety critical system there. So, on which levels can we test? Let's start with a single C module or a class. Depending on your language, this would be a unit test. A unit test essentially really is a test for only one unit or only one C module. You also can test or use a unit test framework, usually for a software integration test, where you bring several C units or modules together, several classes, and make a software integration test. The problem, as you can see, we only test a part of the software, especially the drivers, or for AUTOSAR aficionados, the MCAL, the microcontroller abstraction layer, cannot really be tested with a unit test, at least not in a very convenient way. You would to surround it with functionality, asynchronism, and things like that. And also some of the software units in your application might also not be able to good suited to be tested with a unit test. For example, a motor controller or a battery control, a bus protocol, CAN bus, LIN bus. Those are things that are directly attached to hardware, usually control hardware. So they're using drivers and the like. And also they are highly asynchronous and concurrent. So and that's something you can do not very good with a unit test. Now, let's have a look at the next test level. The next test level would be the smallest possible hardware in the loop test. You can also say a processor in the loop test, where we test at the pins of the microcontroller. So the microcontroller, including the complete software stack and the pins at the microcontroller, that's our black box, and the test interfaces are the pins of the microcontroller. That's the smallest possible hardware in the loop test, and usually it's used for hardware-software integration test. And that's the first level where you actually can test the complete software unchanged of your application. The next level would be a big hardware in the loop test system, including the complete ECU, power electronics, sensors, actuators, and so on. That's already much more effort. You need much more hardware to test this, and so on. And in the end, you run a system test. System test usually is very hard to automate, and you need the complete system in your loop. So including the motor, the pump, hydraulic system, oil, what maybe a human being. So that's usually really hard to automate and really expensive. So with respect to the safety critical tests, what do we do? So let's start with the let's say simplest tests in a way. Those are the unit tests and the software integration tests. They are very good to achieve a high code coverage, which is needed for some standards. But it's not good to test complete software functionality, because you're always only testing a part of your software. Even if you make a complete software test of all your units, in an embedded system, that's just not enough. You still have those integration things, drivers and things like that. You cannot test on that level. So the highest level, so the big hardware in the loop test, this would be the system hardware in the loop test or the real system test. Here the effort is very high to deeply test your software functionality. So if you're talking about software functionality, you're already very far from your software. There's a lot of electronics, a lot of system in between. So it's really problematic to test deeply, and also to test unhappy paths. Because, for example, if you have a variant in your hardware, you need a completely different test setup hardware from the hardware side. If you want to test an unhappy path, you even might have to destroy your hardware, destroy a motor, destroy cables, destroy whatever, to test the unhappy path. That's not really good to automate, to repeat, so it's not reproducible, and so on and so on. And the effort is very high, and it's very late in the process usually. So what we do usually to have a very good coverage for the application functionality on the right chip is to use a hardware software integration test. It's very good to test the complete software functionality as a black box, or no changes, which is important for safety critical systems, including all the error paths. Since we simulate the hardware that surrounds our embedded system, we can bring the system into any state we want to test, including all the error paths, because it's only simulated hardware. So if there's no motor attached, if the motor is simulated, we can break it in any way we want. And that's very good for deep tests. So we can test all the error paths as well, all the unhappy paths. Now, let's have a look at what is needed to test components in general. So here in the middle, you see the system or component under test. That's what we test. That's the object of test here. Then we need test cases, obviously, but that's not enough. We also need stubs, mocks, closed open loop simulation. So we need environment simulations in a sense. If you let's have a look at the component test, unit test, for example. If you test the interface of a C function, for example, you might have 5 functions you want to test, so you need 5 test cases, maybe more, maybe less, depending on the test setup you have. But if you pull out your component test and put it into your test system, you find out that there are actually 300 includes attached, and I don't know how many function calls. And if you want to run an isolated unit test, you need to mock or stop all those functions that are called from your system under test or from your component under test, because if you don't do that, you can't even compile your test. And that's in many cases the bigger problem than writing a test case. So, and this all together is called the test harness. So you create stubs and mocks for unit tests so that you can compile it, and the mock would give you the ability to small simulation ability. So that's used for unit tests. So unit tests are usually synchronous. So step by step, they are waiting, they are blocked until your system under test or your component under test returns. And you need stubs and mocks to simulate the environment, to satisfy the interfaces and so on. For the higher test levels, we usually have an asynchronous system, so we need asynchronous tests. So the test cases can trigger something, and then suddenly 20 different things happen in your system, and you need to collect them and evaluate whether they are all okay or not. That needs a lot more infrastructure, so a lot of concurrency here. And you need usually open and closed loop simulations here, so you do not get away with just stubbing or mocking single functions. So you need a real environment simulation. For example, if your system under test is a motor controller, you need to simulate a motor, because if no motor is attached, your motor controller will immediately find out that the signals are wrong he's getting, and is going to an error state. So you do not even get to the state where you actually can test something. So you need to usually a closed loop simulation for motors or for batteries, for example. And in most cases, you get away mostly for the complete rest of the environment simulation. You usually get away with open loop simulations. For example, the environment temperature sensor, you do not need a model for the environment temperature, because that's just something you can define in your test case. So for the control loop in the core of your application, motor control, you need a closed loop simulation. So that means if your controller changes the speed, the simulation has to follow. If it doesn't follow, you immediately go to an extreme state with your controller and you run into an error. So that's the closed loop situation. And the open loop situation, for example, for a temperature, environment temperature, you would define boundary values or equivalency classes to test. So you make -40, -41, -39, 0, +1, -1, and so on. So that's how you derive test cases from your boundary values, and you can give them directly to the open loop simulation. That's really simple to do. So that's what you need. So you need a test harness for those things. So now for the test harness, we need certain things like simulations, stubs, mocks, and so on. So you need more than test cases. Now, how do I simulate the environment for unit tests? A unit test directly on interface level of the programming language, that's what it usually is, directly calls functions. So it's synchronous, sequential, not concurrent, no states or history usually, and to get to satisfy the interfaces, you have the ability to create stub functions. Stub function or stub object is usually the simplest possible implementation of an interface. If it doesn't return anything, or if it just is a void function, you just get away with an empty function so that your compiler works. If it actually does something relevant for the test case, like returning a value or changing a value, you need a very, very simple functionality to satisfy the test case here. A mock function or mock object usually is already a simple simulated object to mimic behavior at the interface, so that you can run a bit more complex test cases. But it's still a very, very simple simulation. So in general, unit tests are much simpler. So it's very good to use unit tests. Don't get me wrong here. You can overdo it if you strive for 100% MCDC coverage for everything before you even start to test your system in reality or an integration test. That's maybe overdoing it. So now, how do I simulate the environment for hardware-software integration or for system tests? They are basically similar because they are usually both hardware-in-the-loop tests or processor-in-the-loop tests. They are both asynchronous, and they test more than just synchronous function calls. So integration or system tests are usually implemented as in-the-loop tests. So model-in-the-loop, software-in-the-loop, processor-in-the-loop, hardware-in-the-loop. They use those open loop simulations and those closed loop simulations I mentioned before. I already explained this. Now let's have a look at where the different test approaches are located. So in the development process, usually in the early stages, mostly the unit test is used on pure software components. And in the later stages, you might have a big hardware-in-the-loop test system or a system test. So they are usually very late in the process and hard to automate. So the response times are usually not so good there. So with the mini-HIL, we focus on the hardware-software integration test. So the processor-in-the-loop test, usually we run this on an evaluation board or on the real target processor, sometimes also on the ECU, depending on the test setup you need. And here you see you can test a completely integrated application. You can also only test your drivers or only your hardware-related software components. But the sweet spot is really to test a complete application because you get a really good coverage for your application system, so for your system application. So why so hard to HIL test for embedded systems? So let me give you an example again. That's the same example as before. This oil pump, lubrication pump for cranes, for oil rigs, for airplanes, and so on. That's a real customer project. And they need to do a temperature shutdown for all boundary values for 300 relevant system states. It sounds a lot, and it is a lot. So what they had before, they had a climate test chamber, 2 by 2 meters, really big. They put their pump with the hydraulic system, motor, and everything in there, and they controlled this with a couple of scripts. The problem was that it would have taken around 30 days to run all the test cases, and because a climate chamber is a very, very slow thing. For example, to get from plus 40 to minus 40 degrees, it needs, I don't know, 2 hours, 1 hour, 5 hours, something like that. So we're measuring the time there in hours. And so if you take the combination of all boundary values for 300 relevant system states, it's clear why this takes a lot of time. Additionally, you have a lot of hardware in the loop, like a hydraulic system. So the oil gets frozen, or you run out of oil, or some whatever situation, and suddenly your test stops. And that's not what you wanted to test. You do not want to test that your oil freezes at a certain temperature. You want to test the software that's here on the system or the system behavior. So that's why we replaced this with a processor-in-the-loop test, with this mini-HIL test, where we take only the microcontroller, simulate the complete environment. So everything you see here is really simulated, and we test against the simulated environment. And suddenly you get down to 50 minutes for a complete regression test of your complete software, not only for the safety relevant states, but also for the complete rest of the application. And this runs completely automated. There's no hardware that can actually break. If you wanted to break, you change the simulation for error injection or for failure injection. So what can you actually do with this hardware-software integration test? The main goal is here not to test a single software component, but the integration with this component into the software system, including all the drivers and electric signals. You can put your system into almost any state to test it by just changing the simulation for failure injection. So in your test case, you say, okay, now this wire XY is broken, or your motor is too slow, too fast, too much induction or whatever. This enables automation, speed, and depth in your test process. Let me give you an example for how a test case might work for the example from before. Again, the shutdown for the temperature. We want to test our black box, the microcontroller, including the complete software here. Now, we can stimulate the failure by failure injection. So with an analog value like a DAC, we stimulate the ADC in the microcontroller with a temperature value for, I don't know, -50 degrees, for example. Then the black box behavior cascades through your system. So that's what we do not look at it, because it's a black box test usually. And then in the end, what we really want to know on a microcontroller level, on a system level, in this case, we want to know that the PWM goes off after 100 microseconds because it's safety critical. And at the other end of the application, we want to know that the write can message informs the crane or the oil rig or the airplane that the system is broken, or that the temperature is too high, or whatever it is, because the pilot or the surrounding system, the crane, needs to react on the fact that the lubrication doesn't work anymore. This is extremely safety critical. So that's what we can do with such a hardware-software integration test. So now the advantages for safety testing on microcontroller level are: you can test your software system as close to reality as possible without actually really building up a real hardware system. You can test the complete unmodified software with the right target compiler on the real microcontroller, including all your drivers. And that's, for most cases, or for many cases, the most important test for safety. The test includes the drivers, and you can also run a code coverage during integration tests if that's an issue. Usually during the integration test, the code coverage is nice to know, but usually not necessary for standards, because you do not get 100% of code coverage, however you measure it, on an integration level. That's something for the unit test level, but it gives you a good feeling about what is actually covered by your integration test. And so you can find some gaps in your testing strategy, or some things you can't really test on that level, and for them you might need some more unit test coverage. So those tests can work together. Most complex problems, at least most complex software problems or integration problems, can actually be found on this level. So that's very important. There are many errors you cannot find on unit test level. And you have a very good automation with continuous integration, because you simulate the complete environment. In system or ECU level tests, many errors cannot be tested without destroying or modifying the hardware. And you can test most error paths on black box level by just fault injection in the environment simulation. Now, what about some strategies for certification or qualification for the test tools? If you have a safety critical system, you might need to prove that your test tooling works. That's where you need the tool confidence level, depending on the CCL. And the domain, you might need to qualify your test tools. So usually test tools need a lower level than development tools in most cases. The certification of a complete test tool chain is very expensive, and it needs to be redone for every new version. So that's usually not an option for a tool company. So that's why we usually go with tool qualification. We have a project-specific tool qualification, or we have a generic tool qualification kit. It can be standardized to a very high degree, and we can fill the gaps in the project with some specialized tests. And it's proven in use. But only proven in use is, depending on the domain, not always the best argument. That's what this qualification support kit looks like. We have templates with the process that helps you with your process that can be adapted to your specialized process. And we have all the proof that the qualification tests have been executed for, let's say, 80% of what you need, because there are always customer or project specific interfaces. And of course, we cannot give you test cases for that, but for the rest, we can give you test cases. So you can speed up your qualification process with this. Now, let's have a look at the technology we're using. Our motto is here, keep it as simple as possible. That's the HIL hardware platform. Here you see the system under test. That's a microcontroller on a standard evaluation board of ST microelectronics in this case. We have many other adapters for all kinds of other microcontrollers. So basically you can run every microcontroller-based test on the system. The blue board is our HIL. We connect the pins of your microcontroller over this patch panel with our I/O system on this other microcontroller. So, and here we have the original chip, like in this case, in a Kercher machine, in a cleaning machine here. So that's the system under test. The test interface are the pins of the microcontroller. Those pins are mirrored here and here. So that's why we can connect it to our test system. And on a test system, we have a digital twin, virtual twin, environment simulation, however you want to call it. That's the somewhat bigger effort to really simulate the motors, the batteries, the cables, the bus protocols, and so on. We have a lot of predefined modules for that. So you usually do not have to redefine or define your own environment simulation completely. You can take building blocks. And that's the bigger effort. And the usually a little bit smaller effort is to build actually test cases on top of that. Now, when you already have defined the environment simulation, for example, in the second project, or if you want to dig deeper with your test cases, you can, the effort goes more and more into the test cases and less into the environment simulation. So usually you get more and more productive there. You can use digital analog signals, SPI, I2C, CAN, LIN, all those low-level signals, PWM, of course, CentBus, and many more protocols can open. So depending on your domain, we have various software and hardware adapters for that. Now, as I said before, the biggest problem is not the test cases, but the environment simulation. And to build everything together, we have a model-driven development environment. It's based on the language real-time object-oriented modeling. So it's somewhat more formal language than, let's say, UML or so that we can generate complete code out of that. So you describe the structure and the behavior of your test cases and of your environment simulation with models. Then we generate the complete C code. We compile it, we flash it to the microcontroller of our test system, and then we run the simulation and the test cases. Why don't we run this on a PC, for example, or on a laptop? Because we need really hard real-time. For example, to simulate a motor for a motor controller, you need 20, 30, 40, 50 kilohertz hard real time. If not, your motor controller will not work. So, and that's something you cannot do on a laptop with a big operating system. Even with Linux real time, you cannot run this. So that's why we have this microcontroller solution, and it's connected to your laptop or to your continuous integration server to communicate everything. And while we run the test cases, you get a test log. We convert the test logs into meaningful diagrams. That's very important because as human beings, we understand those diagrams much better than a text log or a bunch of text files. So that's for me always very important to understand what actually happened. Here you see the test failed as a sequence diagram. So that's the sequence diagram in the specification of your test case. And that's in the actual logging of the test execution. Now you learn and iterate, and yeah, you move on. If you have a bigger system or more developers or more projects or a distributed team, it's always good to have continuous integration with staging for robustness tests. So how does this work? On every change, your continuous integration server executes the build and the test cases on the mini-HIL board. So for example, those are 8 different projects attached to a 19-inch rack or stored in a 19-inch rack. They're attached to the continuous integration server. And whenever your project is committed or pushed, your project is executed on this mini-HIL system and running the complete regression tests. That's very important to run the complete regression tests, because you might always have side effects. Even if you did not change or touch a piece of code, there might be still problems by any other change you made. It's also important if you have longer running tests. So for example, your requirement-based tests, your use case scenarios and so on, or the failure injection, they usually run within minutes or maybe half an hour, something like that. But if you have a longer running stress test for your robustness tests, for your safety critical tests, you might want to have test cases that run half a day or overnight or something like that. In that case, you build a second stage in your pipeline. The first stage gives you, after 10 minutes, an answer that your commit actually worked and that the most important test cases worked. Fail fast is the motto here. And later the day, overnight or every 2 hours, you start your robustness test that takes longer. That's very important because you want to fail fast. Only if you fail fast, you can repair your system fast, commit it again before it runs into a merge conflict or a test conflict with any other commit your team made. So this way, every code change of every developer of every project is tested on every commit. That's what we favor here. Longer running, as I said, let it run overnight or at the weekend or every couple of hours. So another topic is if you need to create many test cases, especially for testing the robustness of your system, you need a lot of test cases, a lot of different situations, a lot of combinations, different paths, and so on. And that takes a lot of time and a lot of effort, and manually you almost cannot handle that. That's why we have a method implemented. It's called state transition tests. If you do a formal test training, for example, the certified tester foundation level, you will learn about state transition tests, but there are actually almost no tools that really help you to do this. So we've integrated this deeply into our modeling suite. So here you can create a black box specification that tells your test system what do you expect of your system under test. What's the expected behavior of your system under test? Declarative as a state chart. So, and now every path through your state chart from initial to end is a test case. So that's a test case, that's a test case. Even that's a test case, so it makes a loop. And we have a method to generate this, not only as a documentation, as you can see here, but also as code, executable code. So the left thing you must design, but you can imagine that's much faster to design than to create all the test cases. And here you see all the combinations of paths and parameters and so on. You can test, and you find a lot of race conditions with that. Actually, not a lot of race conditions. You find things that are really hard to detect. Errors that happen once a year for one customer, things like that. Not everything, but a lot of them you can detect on that level. So it's really good for robustness testing and for safety critical systems. So I've brought a little demo for you just to give an idea about the tooling, what it feels like. I have a little microcontroller on my test system. So here you see the actual setup of my test system here. That's the system under test. That's the test system, the wires, and the connectors connect 3 PWMs, Hall signals for a BLDC motor control, a temperature sensor, and a little bus system, in this case a UART, could also be a CAN or a LIN. And on signal level, those test cases look like that. Here you see the PWMs, here the Hall signals, and so on. And you can watch it while it runs. That's actually a Salary logger, so a logic analyzer. You can attach this to your system and look at the test cases on electrical level. For example, if you really want to know what your PWM on electrical level did. Here you see the different test cases where they started, temperature equivalency classes, and so on. Now, I jump briefly into the development environment. So that's Eclipse-based development environment. We are currently releasing the first version of the Visual Studio Code version. Here you see the IOs, those map to those wires, so PWMs and so on, analog, digital. So we connect them with the environment simulation. That's an open loop simulation for motor temperature. That's a closed simulation for a motor simulation. So in this case, that's a state machine. So you can actually program directly in the state machine here. So you see all the signals you have and so on, and then generate C code from it. We also have the possibility to integrate generated code from Simulink or other toolings. We also have our own flow chart for to generate simulations and the like. And here on top, you have the test cases. So the test cases, again, are also behavior, but they are different behavior because a test case just behaves a little bit different than a normal program because you have one strict path, but still you need to be asynchronous. And that's what we did here in this language. So for example, if I define the test step, I set the direction, I change the direction, I change the speed here, for example, I get the diagram, what I actually, that defines or shows me what I actually do in my test case. It's rendered automatically. On the lowest level, that's not so interesting, but if I go a level higher and have, for example, a look at those test sequences, or even the test suite, there you can see what your complete test suite does. And it's a flat world here. That's the hierarchical world because you need to see the context if anything happens. So now let's execute this one time and see what happens. While the test case is running, I'm removing this wire. It's a UART wire. So I wanted to remove this to show you that we actually produce an error here. So I prepare this again. Now the combinatorial test cases are running and the heartbeat test is running. Here you see the results of your tests. And if I click on, for example, on the first failed test of the timeout in activate motor control, I click on this element on the error, and in the development environment shows me directly what happened here and where. And if I need the context, because that's a reusable test step, I have the complete context here. I know what happened before. That's very important to really find the problem. Usually need the context where the problem occurred. Okay, so that was the demo. Thanks for your attention. If you have any questions, don't hesitate to contact me directly or Oliver Güth at Hitex, who's responsible for the Hitex sales and projects of the mini-HIL. Yeah, so that's it for today. Hope to see you soon in the next webinar. Back to Anna. Thank you.
Thank you, Thomas. Thank you. This was really insightful. Thank you also to everyone in the audience for joining us today. Thomas and the Hitex team will answer all your questions via email, so keep an eye on your inbox. We will also send out the presentation slides and the recording via email. And as always, you can find all our webinar recordings on the Hitex YouTube channel. Thanks again for your interest and participation. We hope to see you again at the next event, maybe with the next event with Thomas about architecture-driven development for embedded systems. You can find the registration link in the chat. Have a wonderful day, everyone. Bye.